Okay, let's talk. So you should have known what to do. And I have evidence to support the idea that most of you have no idea what you're doing. I mean, the video was confusing. Everyone in the room was loud? That's probably my fault. That's sarcasm. Why were you loud? So that you could get the mode being 0%. I'm going to be gone for a week. Monday, Tuesday, Wednesday, Thursday, and Friday next week, chilling with some people. And you're going to have some videos to learn from. And that's weird, but I'm going to expect you to have learned from them better than 39%. So we better talk this through. 57% got that right. 52, 24. Ooh, so we suck at math. 24. Yeah, well, we could do better. No answer. Nice work. Okay, these are the easy ones on this chapter. So please make sure, like for real, they're the cakewalk before you get to the hike. So we really need to make sure we know what we're doing. Now, if you got 100, that's great. If you didn't, I don't think you're a loser, but I'm frustrated that your explanation was, oh, well, we didn't pay attention. How many examples did I do in there? Do you remember? Only 2? Okay, there's probably more than. Okay, please pay attention. All right. Whoops. Where are you? Oh, you're in front of me. Okay. Now we're going to, thank you, sir. Should I refresh the statistics or just leave them how they were? Right, so we should refresh it. That's a 75. That would bump a 39, probably up all the way to a 42. So I feel better about that now. We're at least in the 40s, which is how old I am somewhere. How about me 20 years ago being thin? You know, the assembly, that was pre-driver's ed, Tom Davidson body in that video. How many of you have seen Night at the Roxbury? 0. No, we were doing the dance from Night at the Roxbury. It's 2 brothers that like. Yeah. Anyway, it was stupid. Moving on. Okay. Using the table, what is the exponent of Nh3? Okay, it's kind of like voodoo magic here, but once it clicks, this is not super hard at all. So if we're looking for Nh3, we're looking for a time where BH3 is held constant, but Nh3 is changed. You with me? So these two, BF3 is held constant, and you can say that this one's half of that one, but that would blow your minds. I would say in this experiment, this one is 2 times what this one is. Are you okay with that? Okay, so the process to answer these problems is pretty simple at the start. You look for the one you're looking, and the other one has to be constant because it's science. We're trying to figure out exactly what one change does. So we have to hold something constant, and it's the one we're not looking at. So BF3 is held constant, NH3 is doubled in one versus the other. And now we look at the rate. So the rate here is a 1, and the rate here, well, 0.1065, and this is 0.2130. So I'm going to put a 1x here, and I'm going to put a 1x here, because when I had it a 1, I got a 1. You don't have to do that, but I'm going to. Up here, when I doubled it, this also doubled. You with me? So I doubled the concentration, and the answer was double. So that means this exponent has to be what number? A 1. 1 means I don't really do anything in the middle. Okay? If this did not happen, but if I doubled and this became 4, then I doubled the concentration, but my answer was quadrupled. And they're like, okay, how does a 2 become a 4 in exponent land? Then it would have been squared. Go ahead.
What happens if like it's 4x?
If this is 4x, so I quadruple it. And then if it's squared, the rate would be 16 times. If it was a 1, it'd still be just 4. So if the change does the exact same change to the rate, then the exponent's always a 1. Can we say that again? So if the change, which was to double it, is the same thing that happens to the rate, it doubled, then the exponent or the order of the reaction is a 1. So far, sort of lost. Okay, so the exponent for NH3 would be a 1. So in my rate law, we would say that we put it in brackets and this would be raised to the first. Fair enough? Okay, then it's the same experiment. Now we're just asking about BF3. So now I want this one to be constant over here, and these are. And so I look and we have 0.2, 0.350, or 0.175. Which two would you choose to compare? All right, these two. I mean, you can do 7/5 and 5/7 if you feel like it, but that's just what like psychopaths would do. So here we have a 1, and then this is times 2, right? So I tried this experiment and I doubled the initial concentration compared to that one. Do you see what I'm saying? But my NH3 is held constant, which is what I want, because I want to hold it constant and see how the change affects the rate. With me? Okay, looking over here, this was my 1, and this number is roughly what? 2 times, right? And so if what happens to the rate is the same as what happened when you changed, then the exponent would be what? It'd also be a 1. Fair enough? So we would say in chemistry language that the order of reaction with respect to ammonium would be first. With boron trifluoride, the order of the reaction would be first as well. Now, the overall reaction would be what? Remember that? It's second order overall, because you add the exponents. Not sound familiar? Okay, I may not have. That's fair. Okay, now it didn't ask specifically, but what would the rate law be now? It would be rate equals K, because K is the constant that's just always there, right? Then we have the NH3 concentration, and it was raised to the first power. I learned that because if I put a 2 in here, it generated a 2. So it must be raised to the first. And then I had BF3, and it was also raised to the first. That would be the rate law, the general rate law with no numbers in it. Did I talk about writing the rate law from binding exponents? Okay, we will need that coming up here. Oops, wrong direction. Okay, using the information from the previous 2 problems, what's the value of K? I need a screen with K on it, or the value, so I'll come back here. So we're solving, we know K equals, sorry, we're going there, but first I should write rate equals K times the concentration of NH3 to the first and BF3 to the first. All right, This is really simple algebra once you know what you're doing. We want to solve for k. So I'm going to put the k equals, and I know rate is on the top over here, right? Because I can just see rate equals k or k equals rate. But I need to isolate, or I need to get these on the other side. So they would go in the denominator. Fair enough. Okay, then now that I have what k equals in words, I pick any row I want, and I always pick the top row so I don't just randomly screw up. It's like when you sing a hymn, 2 and 3 are like impossible to sing. I don't even try. That's where the alto lines come in for Tom. All right. So I just plug it in so I don't screw up. So I know that now k equals the rate, which is over here, 0.2130. And then NH3 is 0.125. And it's just raised to the first, so I'll just leave it alone. I guess I said that and then I did it anyway. And then 0.250. You just pick one. And I did it wrong. I just said don't screw up, and then I did it, didn't I? I did the second one. All that story for fun. These two. That's convenient because they're just the same number. Sorry. Yeah, you got to pick the same line for all the numbers. After all that story, and then I still screw up. And there's a good lesson on Tom Davidson's not perfect, just perfect looking. So 0.2130 divided by 0.25 squared. And what was it? 3.4. That would be K. And it has a big, ugly, like, unit that goes with it, but we're just going to type in 3.4. Fair enough? Uh-oh. What'd you get, Brittany? Okay. All right, let's test it out. Someone choose this line and see if you still get 3.4. And you got 3.4. Okay, we could choose any of the lines. Just don't cross like I did, which is super embarrassing. Okay. Then the last question, I don't even know. What did it ask? Let's see. Ooh, this is good. If a sixth trial was performed and the concentration was 1.85 of this, or 0.185, and 0.275, what would this be? Okay, we know the equation now. We know that rate, which is what I'm going to solve for, equals K times, NH3, getting sick of writing this, and BF3, right? And so we just plug it in, rate. Oh my goodness, Tom. Equals 3.4, right, sorry, times 0.185 times 0.275. And I don't know, what do we get? 0.173? Okay, probably right. These are not awful typically. They're not bad at all. Okay, let's try some more. Hopefully I have some in your future here. All right, did you do this one? Does it look familiar from yesterday? Yes. I got one no and a bunch of yeses, so I'm going to go with the yeses. Did we do this one? Okay. Some of these might be complicated. I haven't looked in advance. Instead of getting prepared, I talked with Bert in the hall the whole hour, reminisced about the good old days. Emma Smith. Okay, give this a shot. We want the rate law, the rate constant, and solve for X. Sound fair? Give it your best attempt. True, but I mean, you're up there in the top 10. I have like 6 members of my family. All right, so this is how we find the exponent. Right here, these two numbers are held constant. So I can use these two trials to figure out how changing NO2 affects the rate. So I can use these to figure out how this is constant, how these change to figure out NO2. So I look at them, and if you're confused, just divide the big number by the small number. Now, most of you probably know that 420 is twice as much as 210, right? So from trial 2 to trial 1, this will say is the standard of just 1 or 1 times. And here I doubled it. Okay, so in this trial, I double the concentration of NO. I hold the concentration of N2 constant, and then I see what effect that has on the rate. So this one is our standard. So I'm going to say this is just 1. And then I look and I need to know how this is changed compared to this. And usually it'd be like 0.68 or something like that, right? It doesn't look like that, but it looks like it's roughly 4 times more. And to confirm that, just take this number, the big number, whoops, I don't know why I did it above it, and divide it by the small number, and you'd get pretty close to a 4. So when we doubled the concentration, or when I doubled this concentration, with me, the rate ended up 4 times more. So I'm not putting another thing here, I'm using the exponent. So what exponent makes a 2 become a 4? 2, if I square it. Are we okay with that? So based on the change that I made and the change, the adaptation that the rate had, I know that the rate law for, or the order for NO is a 2. Kind of? Okay. Now I need to look, and we'll look at this one. Right here and right here, those are held constant. So I can use these two to study. So I have the 2 constants, and then once again, luckily for us, it was just doubled here. This one is 2 times this one. Okay, now don't consider any of this anymore. We're looking all here. So now I look at the rate, and this is still my standard. It's a 1, and I look down here, and that looks pretty close to being 2 times more than this one. If you had any question about that, you would take the bigger number and divide it by the smaller number, and that would give you 2. Okay, so since this time my concentration was doubled and my rate was only doubled, then there is really no exponent, or it's a 1, because a 1 just means you multiply it by 1. So now I know that the H2 order is a first order. Okay, I'm going to get rid of a ton of this. So it'll be third order overall. So the rate will be equal to K times NO, and I already forgot which one was that one, 2, and H2 to the first. How many correctly had that written? Raise your hands. Okay, I thought it'd be higher, but like we can work with this. It's not a mega disaster. Just, it's like a category 3 hurricane. No one even left their house. Okay. Tim, I've been in them. They're not that bad. Now, 4s, you go 5, sayonara. All right. Now, I need to know K. So K will be equal to, you won't like this, but I'm going to say rate divided by NO squared, H2 to the first. You okay with that? So now pick a line. Who wouldn't pick the 420 line? I mean, let's be realistic here. K is equal to the rate, which is 0.1360 over NO, which is 420 squared, and it's 0.420. And 0.122 held to the first. Now, a lot of times your calculator really lets you down here, and you're like, stupid calculator. But really, it's stupid you. I'm sorry, it's not it, it's you. Make sure you do all this denominator in a parenthesis. If you don't, you'll get it wrong, because you're going to find, you're going to take this, you're going to divide it by 0.420 and square the answer, and then you're going to multiply it by that. Like, you're going to be so far off. So when we correctly type this in, anyone have K for me? 6.32? All right. And now I have to solve for X. So I know that the rate is now equal to, I'm going to choose the bottom line. So I know it's equal to K, right? 6.32 times 0.105 squared times X to the first. Did I write that all in right? Okay. Oh, I had the rate. I had that number. 0.0339 equals all that. So I'm going to divide this by 6.32 and 0.105 squared. And I end up with a number. Healy, what'd you get?
0.4865.
We agree with that value? Okay. If we care, we should look up and we see the unit is mole per liter, so molarity. Okay, who had 0.4865? Raise your hands. Keep them up for a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we're about half. So not awful. Hopefully I have more practice on the next one. Okay. Well, let me double check this one. This one might be, I know there's one of these that has a landmine in it, but this one's a little harder. Anyone already know why it's harder? Because y is never held constant. Let me see if I have an easier one before we do that one. This one's got to be easier. All right, you can do this one. Yeah, like it's doable. I got the rate law already done just in my head. And I'm not like a super genius. I bet someone else has it done already. Oh, maybe I am a super genius. I should donate my mind to science. They'll reject it. Okay, I'm going to pause this. My two friends make. All right, here we go. Okay. I usually start left. I see this is constant. So I'm going to compare these two. I'm not going to worry about the middle yet. Okay, so here we go. Which chemical am I studying with these two experiments? O2. All right. The one I'm changing is the one I always get data from. So these get a little tricky. Make sure you look at the exponents. They're really, really important to make sure you check the exponents. These are both 5. So since they're both the same exponent, we could really just look, hey, it's a 2.5 and a 5. You all right with that? So down here between these two, I doubled it. From here to here, what happened to the rate? It doubled. So what exponent really does nothing? A 1. So the exponent for O2 is a 1. With me? Okay, who had that part? Let's all raise our hands, hopefully. All right, good. Let's get rid of all this then. Okay. That was the longest erase ever. I was reading, someone Venmoed me. I was like super excited. isn't excited. All right. Here, this one, they're on top, so they're not bad.
Oh, what is that?
So from here to there, that was a 2x. I doubled it. From here to here, what did I do? No, the other way around. It's 4 times greater. So what exponent turns a 2 into a 4? A 2. So NO would be a 2. Who had that? Uh-oh. No, it doesn't matter. So rate equals K times this, right? It never asked any other questions, but it could. Yes, Seth. I'll see you guys a week from Monday. What? I will.